Hatfield, October 2000. One of the worst train crashes in recent history killed 4 and injured 102 people. Nearly 2 years earlier, engineers had identified a form of fatigue known as gauge corner cracking in the rail, which eventually broke and caused the crash. Since Hatfield, the pursuit of safety has become even more of a concern for the rail and train operators, but checking thousands of miles of track for defects and wear and tear is a slow and costly process. However, soon every train, whether high-speed mainline or a local service, passenger or freight, could be carrying a device that continuously checks the rails for defects, no matter how fast the train is travelling. Even the Japanese bullet trains, capable of speeds of 300 kilometers an hour, could use this detection system when fully developed, because the ultrasound waves it employs travel at 3,000 meters a second. This new technology is the brainchild of the University of Warwick's Physics Department, which has just been awarded funding from the Engineering and Physical Science Research Council to develop their discovery from the lab into a device that can be used in the real world. Dr. Steve Dixon and colleague Dr. Rachel Edwards have taken a pair of electromagnetic acoustic transducers which generate and detect ultrasound waves and found a way to propagate a wave along the track from which they can measure cracks and defects faster and more accurately than existing systems.
Firstly, the approach we're using here is non-contact. This means that it's much more practically viable to operate the system. There's no need to maintain good contact with liquid couplants. Because we're using a separate generator and detector, we don't run into the same physical limitations of the inspection speed of a conventional system, which may be limited to doing inspections online at around 30 miles an hour.
Gauge corner cracking, small fissures in the rail surface, which were the precursor to the Hatfield crash, are one of the problems detected by this method. To test its accuracy, they've created cuts of measured depth into the rail surface. Then they generate an ultrasound pulse along the surface of the rail and record its behaviour on a computer. As the detector moves close to a defect, the surface wave reflected from the defect can interfere with the incidence wave to give a larger amplitude signal. However, at speed, the most reliable measurements are made on the portions of the wave that have passed under a defect. This is an accurate method as the defect can be detected anywhere between the transducers during the measurement. The wave used is termed wideband, containing many frequencies in a single pulse, and how the defect changes these frequencies and the amplitude of the wave are both measured as it passes through a defect.
A good analogy to use is that we have a piano. We hit all the keys at once. There's lots of different frequencies there. We use a program called a Fourier transform to break that down and tell us what frequencies are present in the pulse. With the waves that we're looking at, lower frequency waves travel to deeper depths. So if we can break down the wave into these different frequency components, we have another means of saying how deep the defect is by looking at the proportion of the wave frequencies that can sneak underneath the defect compared to those that are blocked. We can combine that with just the amplitude measurement. So if you like, we have two ways of checking and giving us information of the depth of the defect.
In order to be certain of the way the wave behaves, they use a laser Michelson interferometer, which measures surface displacements down to a size smaller than an atom, to take a series of measurements of the rail in order to build up a highly accurate image of how the wave behaves, which they've animated on a computer. Having proved their discovery, the next step is to build a device that will work on a train.
We're hoping that the companies that have already committed to involvement with the project, such as Network Rail, London Underground, Serco Rail, and a couple of SMEs, in addition to the rail manufacturers Chorus, that will be able to have a very rounded and good overview to what's required from the industry. We want to take our research from the lab and put it into the real world and make something that's useful for these people.
If they succeed, they can transform every train in the country into a highly sophisticated rail monitoring system that routinely examines the tracks for any potential defect, radically improving the safety and efficient management of the rail network.